So we got the first situation. The question is, when you flip a coin in a plane, why doesn't the coin fly backward and get left behind? And we got a bunch of your answers. The coin is moving forward along with the plane, so due to the inertia, it keeps doing that because nothing is stopping it. That sounds pretty good. Actually, that's even a good start here. It has the same horizontal velocity as the plane, so instead of getting left behind, it moves forward. Okay, so one uses the idea of the x velocity like a projectile. The other one uses the idea of inertia, and it continues on with its inertia. I like that. Two different perspectives. One's Newton's first law, one's projectile motion. It's not just the plane that has velocity. Everything in the plane has velocity. I really like that one. You know, like if you're inside of a car, doesn't the air inside the car also have velocity? And so in terms of relative motion, we talk about airplanes in the wind, the air is moving along with us. So now we've got the idea of projectiles, we've got the idea of inertia, we've got the idea of an object in a medium, like a coin being flipped inside of the medium of air, which is in the car. That's a lot of cross connections. Next one, it doesn't go backwards because the inertia of the coin carries it forward. Okay. The coin is already traveling at the speed of the plane. This sounds like projectile motion. Now, as I flip through these guys, and I can put down a few of them, and you can read them faster than I can, but you notice that we have people either talking about relative motion, or they're talking about projectile motion in the x velocity, or they're talking about inertia, which happens to be the topic that we're discussing right now. And the nice thing about this is that it sort of unveils that we have multiple different ways that we can talk about the same thing. And the truth is that we're all kind of correct about it, right? Now, if you're asked in a test, could you please explain this in the context of inertia? You got to explain it in the context of inertia. But if you were just living physics and explaining it to a friend, you might use one of those three main ideas, okay? I like that there are three main ideas there. I want to take a look at the next one. The next one says, why would the actual path be lower in height than the ideal path? Now, I have my own thoughts about this, but I definitely want to see what you guys have to say. This one says, if FA, which is, I guess, F applied. Somebody help me on that one. Is FA F applied? Who is the author? Is it applied? Okay. If FA is greater than FG, then it would be the ideal, but it's weaker. Okay, so the applied force only really happens right there at the blast off. The applied force doesn't travel with the object. And so that's something that we talked about maybe at the beginning when we were talking about basketballs being thrown, that the force that's making the thing fly for a projectile only exists right at the launch moment. So we got to be careful about that one. This one, the inertia carries the object forward. Okay. But if there's air resistance, that's that external force, right? That slows it down. So we talk about net unbalanced force. Here's another one that talks about the actual path being lower than the ideal path because of air resistance, reducing its vertical height, and maybe even making it not go as far horizontally. Because of drag, wind, and thrust, the actual path would be lower in height and more narrow. Now, I like the idea of drag and wind because that's going to maybe keep it shorter and lower. Be careful about thrust because that's the same idea as we had before. After the initial launch, there's no thrust. Okay, so a projectile that's being launched through the air doesn't have thrust. If it was a rocket has thrust. It has an internal power source. Projectiles, not so. Okay, so be careful about that one and knowing what thrust means. Inertia. The inertia of the air is 0, and it pushes against the ball. Oh, okay. That's an interesting perspective. I hadn't thought about that. That actually is what drag is, right? Drag is the fact that the air itself has inertia. And because it has, each of these particles has their own mass and their own tendency to stay put, that ball has to deal with the air's inertia of wanting to stay put. I guess I hadn't actually framed it that way in my own mind. So that's cool to see that perspective. And I wouldn't even say that that's wrong. That's just like definitely not how I think. So that is pretty cool. All right, because of other external factors like drag and air resistance, sounds like we've got a recurring theme there. And the actual path is lower in height because it may not have as much acceleration or initial velocity. Again, I think this goes back to this idea that we're somehow thinking that it's connected to what's happening at the beginning. The acceleration is due to gravity. The whole time we got acceleration due to gravity acting on this ball. But it looks like the shorter, lower one also may deal with the fact that it's experiencing drag as it goes, all the way along, slowing it down and lowering the trajectory, right? Whereas the one that's the so-called ideal only has gravity acting on it. And it's not even really ideal, it's actually fake news, because on Earth we're always going to have drag. You know? And we can take a look at these other ones, but I suspect that they all have, oh, there it is, drag, have these key words. Drag, drag, and drag. All right, so most people really hitting the nail on the head there. A few people maybe like with some lingering misconceptions. We'll take that guy away. I want to take a look at this third one. The third one is hard to understand what it is, but just to recap again, we've got a cart, and you can think about like a block of wood, if you like, sitting on wheels, and we have a pendulum that's free to swing that's attached to the top of that cart, and in the background there's a protractor that can measure the angle at which the pendulum swings. So the idea here is that we got to figure out how we could use a device like this to investigate inertia. This one says that it shows the angles that the pendulum turns to. That's true. That's a fact about how this thing operates. It doesn't address inertia, but it's true. That is what this shows. It measures force when you push it. So somehow force might be involved, right? So if I accelerate this thing with a force, how's the pendulum going to move? Off center. Makes sense. Still doesn't quite address inertia though. It says if the wagon accelerates, then stops, the pendulum will continue to swing forward with the velocity that the cart was driving at. That's true. And I think we're just scratching the surface of the idea of inertia. If this pendulum starts going, it gets up to speed, and then you stop it, when the pendulum continue on at that speed and swing forward. And this is a very contrived piece of lab equipment, but from my perspective, you might have something hanging from the rear view mirror in your car. I mean, for me personally, I have a cross hanging from my rear view mirror. Somebody might have dice. Somebody else might have some other decoration or whatever hanging from their mirror. But this is very much like that thing hanging from the mirror. And when you accelerate, it's going to swing one way. When you slow down, it's going to swing the other way. And so really, if you have anything like this hanging from the mirror on your car, keep this in mind, that this is showing inertia, right? This is showing Newton's first law as we drive. Let's see what some other people said. They said, as the cart slows down or accelerates, it can show that due to inertia, the object will want to keep moving at the same velocity, either forward or backward. That kind of encapsulates the idea. And as we go forward, hopefully we'll see a few more. Constant velocity. Will swing back and forth because it wants to keep doing what it's doing. And I think this is something that we have to be careful of, and I do it too. I keep on saying that things want to keep doing what they're doing. Let's not anthropomorphize our rubber stoppers hanging on the ends of strings. They don't have any wants or desires. They tend to keep doing. And I know that I messed that up as well. Let's try and use the word tend to though, okay? Because wanting is something with an inner voice or like a desire to live would do, whereas tending is something that objects can do. And then it could be used to measure the amount of inertia experienced by an object. And that's true, but maybe not terribly descriptive. Let's think about this idea of things continuing in their velocity and maintaining their ongoing motion as a tendency of inertia.